So find the equation of the tangent plane to f of xy equals x squared minus 2xy plus y squared at the point 1, 2, 1. Okay, so I'm saying 1, 2, 1 is on there. So when you plug in 1 for x and 2 for y, you better get 1 for z when you plug x equals 1 and y equals 2 into this function. You better get the z equals 1. So I'm saying this is a point on the graph of this surface. Let's find the tangent plane there. Okay, in order to find the tangent plane, the formula tells you what you need. You need the partials. And by the way, from now on, if you're not sure what to find the partials. You'll get partial credit. All right. Yeah, I know. Sorry. Okay. So what's we already did this earlier, but let's pretend like we didn't. What's the partial with respect to x? Well, 2x is a good start. Minus 2y. But then we need the partial evaluated at x equals 1 and y equals 2. So what's the partial evaluated at x equals 1 and y equals 2? I don't know. If we plug in 1 here, that's 2. If we plug in 2 here, that's minus 4. So negative 2. Would you guys buy that? Right about now, you're all, yeah, whatever. Tired. Okay. And then what's the partial with respect to y? So this guy's 0. So negative 2. Don't we need an x in there? X. Because you take the derivative of y with respect to y, that becomes 1, but you still have the constant of minus 2x left, right? Oh, you mean here? Yeah, yeah. Yeah, my x evolved and it lost its tail. Okay. And then what's this derivative? Negative 2x. So that guy's negative 2x plus 2y, right? But then we need to fill in the equation of the tangent plane, we need that evaluated at the point of tangency at the x, y values of that point. So we plug in 1, 2, and what do we get? Negative 2. When we plug in 1 for x here, and when we plug in 2 for y here, we get, what, plus 4, so 2? Okay. So now all I'm doing is plugging in this equation. Don't forget the minus z naught, right? So this guy, x naught is 1, y naught is 2, z naught is 1. So don't forget that guy. So plug in this equation, we get z minus 1 equals the partial with respect to x, which is negative 2, times x minus x naught, which is x minus 1. Negative 2. And then plus, so that's the first part. That's this part. And then what's the next part? It would be the positive 2 plus positive 2 times y minus y naught, which is just 2. And that's the equation of your tangent point. So in part B, we're going to find a linearization of L of x, call it L of xy, for f of xy at that point of tangency 1, 2, 1. So in the last example, we've got this guy as our equation of our tangent plane. The linearization is just going to be this guy. L of xy is just going to be this guy solved for z. Get z by itself. There's your linearization. Okay? So L of xy then is going to be negative 2 times the quantity x minus 1, just recopying what I have up here, plus 2 times the quantity y minus 2, and I'm going to add that 1, plus 1. And then I suppose we could multiply things out and simplify. What do I get if I multiply this out? Negative 2x plus 2 plus 2y minus 4 plus 1. So let's combine just the constants, right? So negative 2x plus 2y, and then what do we get? Minus 1, I guess. So here's your linearization. It's nothing but the equation of the tangent plane that we just found solved for z. Okay, and the idea is that near that point of tangency, L of x, so let's write this down, L of xy is going to be a good approximation for f of xy near the point of tangency. Does that seem reasonable? Sure, it's just a generalization of what you learn in Calc 1, isn't it? Okay, so that's, I think, all we wanted in Part B. Now, we're going to use that, L of xy, to estimate the function at x equals 0.95 and y equals 2.02. So what would the x and y values be at the point of tangency? The x and y values 1 and 2. So notice these x, y values are close to 1 and 2, and that's critical. Otherwise, it wouldn't make any sense to use L of xy to estimate f of 0.95, 2.02. So make the observation. This is close. 0.95 is close to 1. 2.02 is close to 2. And this is why it's going to be a good approximation. Using L of xy at these x and y values will be a good approximation. So basically, all you have to do is take L of 0.95, 2.02, using the function notation, and then plug in what we got in the last problem. So it'd be negative 2 times 0.95 plus 2 times 2.02 minus 1. And you get, let me write it down, negative 2 times 0.95, and then plus 2 times 2.02, and then don't forget to minus the 1. And if you're keeping score at home, you should get 1.14. I think that might actually be exact. An exact value of L of 0.95, 2.02, if I remember right. So you can check me if you want. Plug it in your calculator. But so this is an approximation of f of 0.95. So we would say f of 0.95, 2.02 is approximately equal to 1.14. How close is the approximation? Well, if you actually run these values through f, it turns out that f of 0.95, 2.02, at least to 4 digits past the decimal is about 1.1449. So we're accurate to the first 2 places past the decimal. Let's let z equal the sine of 2x plus 3y. Let's use dz to estimate the change in z, delta z, from negative 3.2 to negative 2.95, 2.04. Okay, can you tell me, just to see if, check your understanding, can you tell me what delta x is? What's the change in x when it changes from negative 3 to negative 2.95? It's actually an increase, right? What's the change in x? 0.05. Everybody see that? And then when it goes from 2 to 2.04, what's the change in y? Delta y is 0.04. Everybody see how to find those? Just subtract if it's not clear, right? Subtract the relevant x values and the relevant y values. Okay, so if we want to use dz, then we find the total differential. So let me remind you, I know you're a big problem in this class is information overload, so I try to review as much as I can, and it really it slows me down so that I'm always in a hurry at the end of class, but I think it's worth it because you guys need the review. So remember what dz is. In general, it's the partial with respect to x with generic inputs x, y, and then dx, which is the same as delta x, you guys, plus the partial with respect to y, dy, which is the same as in Calc 3, it's the same as delta y. Okay? So what can we do then? What does this formula tell us to do first? What had you better find? If you want partial credit and you have no idea what to do, find the partials. It's easy to remember, right? Okay, so find the partials. Okay, so z is f of x, y, right? Okay, so f sub x at xy is what? Take the derivative just with respect to x, so you think of y as being a constant. So cosine, the derivative of a sine function is cosine. The argument of the function stays the same, but then you multiply by what? By a 2. You take the derivative of the inside function by chain rule, calculus 1 chain rule. The derivative of, with respect to x, of 2x plus 3y is just 2, because 3y is a constant with respect to x. Make sense? Now, we're going to have to put in these particular values. So this negative 3 is like your x naught. 2 is like your y naught. So we're going to actually have to plug in these particular values. So let's do it right here while we're thinking about it. So if you evaluate this at negative 3, 2, right? So you're plugging in negative 3 right here and 2 right here. You end up with 2 cosine of what? 0, I guess, right? And what is that? Cosine of 0 is 1 times 2 is 2. Beautiful. Now, the formula says take the partial with respect to y. So we'll do what the formula says. What do you get? Again, the original formula is sine of 2x plus 3y. So it would again be a cosine, except this time, what would you have out in front by the chain rule? The derivative of 2x plus 3y is, with respect to y, is 3. And then if you evaluate that at the given values of x and y, what do you get? 2 cosine of 0, or I'm sorry, 3 rather. Cosine of 0, right? But that's just 3. So these values were chosen because they're nice, right? Does that make sense? Yes.
Did you say that in Calc 3 we're supposed to look at change in y equivalent or approximately like equal to dy?
No, they're the same. I don't know why I used a wavy sign there, but anyway, no, dy and delta y are the same.
Okay, so you don't plug in 0.04?
Oh, we're just not there yet. Yeah, you're ahead of us. You're way ahead of us. Okay. So now dz. This is dz evaluated at these particular values. Okay, so dz, you could say dz when x is, one notation you could use is x is equal to negative 3 and y is equal to 2. Okay? You could say then when you plug it in, you get the partial, which is just 2, right? And then dx is, what's dx? 0.05. So 2 times 0.05 plus the partial with respect to y evaluated at negative 3, 2, which is 3 times dy, which is 0.04. So there you go, Scott. I think that's what you were wanting to do, right? Yeah. And then when you do that, I think you get 0.22 when you evaluate that. And that's what you were after. Okay, that's all you were asked to find. So you're estimating delta z. This says, in order for z equals f of x, y to be differentiable, It's just saying that delta z has to be a good approximation of dz, right? Again, go back and look at that fraction. Go back and look at this version of the fraction. It's a little easier on the eyes. But it's saying the same thing as the limit below it. It's saying that, oh, if this limit is going to equal 0, then this numerator, both the numerator and denominator go to 0, right? As delta x and delta y go to 0, 0. Both the numerator and denominator go to 0. So this is saying that the numerator better go to 0 a heck of a lot faster than the denominator in order for this limit to be 0. So what's it really saying? It's saying delta z for a differentiable function, again, that's what we're defining right here. For a differentiable function, delta z is a darn good approximation for dz.